Anyway, so let's start. We're happy to have Michael Wheeler broadcasting from Melbourne. That's his first lecture, and he talks about the q-Whittaker polynomials, an invitation to the q-Whittaker polynomials. Go ahead.
All right, so thanks very much to Alexei and Ivan for invitation to speak in this summer school, and I'm of course very sad that we didn't get to go to Oxford, but yeah, and certainly I never expected I'd be giving my lectures from my living room at 11 p.m. in the night, but that's the situation we have. So all right, so so these lectures, I think for a number of people, they will be quite elementary and sort of revising a story that's by now very well known. But hopefully for the newer members of the audience, you can find something worthwhile in these lectures. And so mainly I'm going to be talking about the interplay of integrable vertex models and symmetric functions, which is a topic that I've certainly worked in for a number of years. And I said that it's an invitation to the q-Whittaker polynomials. I realized then when I actually started writing the talks more that to actually get to q-Whittaker polynomials, you have to go through quite a bit of territory. So the q-Whittaker polynomials will certainly be in there, but it might take us a little bit of time to get to them. So, and in terms of probabilistic content, so there won't be so much probability in these talks per se, but sort of the structures that appear in here, Yang-Baxter equation, stochastic vertex models, and also, of course, symmetric functions, all of these are things that are very closely related to the topic of integrable probabilities. So I think just giving exposure to these things will be helpful for people who are just starting out. All right, so today I'm going to be starting off with some very basic stuff. I'm going to start off by defining what are the so-called stochastic vertex models. I'll talk about the Yang-Baxter equation, which is the equation that endows these vertex models with an integrable structure. And then I'll move on to talking about various quantities that you can study in those vertex models, which are the wave functions, and also look at their symmetrization formulas. So that's basically what we're going to be doing today. And then tomorrow I planned to talk about whole Littlewood polynomials and q-Whittaker polynomials. So these are going to be the two families of symmetric functions that are going to be the main focus of the lectures. And also I'll say a little bit about some of their properties, including Cauchy identities, and also how you can derive both of those polynomials or expressions from them, essentially from the wave functions that we're going to meet in the lecture today. So there is a way of taking those wave functions and performing some procedure to it, which is the procedure of fusion. And so, yeah, we're going to talk about that in the lecture tomorrow. And then I'll give formula number 1 for the q-Whittaker polynomials. So I think it was advertised in the abstract to the talks that there were going to be 2 formulas for the q-Whittaker polynomials. So this is going to be the first one. And then in the final lecture, I'll move on to something a little bit different, which is going to non-symmetric McDonald polynomials, how these are related to very important algebra called Hecke algebra, and also how you can express the McDonald polynomials in terms of vertex models that live on a cylinder now. So actually the underlying geometry of the partition functions changes and they live on a cylinder. And then if time permits, we'll get to formula number 2 for the q-Whittaker polynomials. And really, I had hoped that in sort of highlighting the q-Whittaker polynomials, that it might actually sort of heighten the interest in the fact that you do actually have these two formulas for them, both of them using integrable vertex models. But it's not obvious, at least to me, why those two formulas should be related to each other in any way. And so I think that's an interesting open problem to actually look for some sort of bijection between the configurations that you have in those two combinatorial formulas. So that will be sort of an open combinatorial problem that will arise out of these lectures. All right. Okay, so let's begin with the actual lecture. So I'm going to be firstly talking about stochastic 6-vertex model. So I think in Hugo's talks, in his talk yesterday, we would already have seen 6-vertex model introduced. So probably I will just be repeating some stuff here. But 6-vertex model, it's a very old model of statistical mechanics. Originally used as a way of modeling ice crystals. And so we have these 6 types of vertices that are presented here. And essentially what happens is on each of the edges of the vertices, you put some sort of a state. And for the 6-vertex model, the possible states are just going to be 0s or 1s. And they satisfy what is called the ice rule, which is to say that whatever states you have on the incoming edges of the vertex. So here, yeah, I might actually switch to the thing so that I can annotate. Okay. So here, for example, I have 2 zeros. And so these would be referred to as the incoming states for that vertex. And so the 6-vertex model has the property that whatever states are incoming to the vertex are also going to be outgoing. So you have to have conservation of basically the ones that go through the vertex. So here, for example, because I have 2 zeros, the only possible outgoing states will also be 2 zeros here. And in a similar vein, if I look at the next one, I have 2 1s coming in, and that forces the outgoing states here to also be both of them equal to 1. But then we get into these 4 vertices here, which are really the interesting ones of the model. And for these vertices, you see that once you fix the incoming states to the vertex, you actually have 2 possible outcomes in terms of what can happen. So here I have a 0 and a 1, which enter from the left and from below. And its partner is the one that lives over here, actually. So for both of those vertices, we have the same incoming data, and you see that there are 2 possible ways that the 1 can leave. So either it leaves via the top, or it will leave via the right edge here. And so actually, those 2 vertices are paired with each other, and I'm going to give them these labels here, B plus and C plus. They both have the label plus because they're going to be partners. And in a similar vein, the other 2 vertices are also natural partners of each other here. Once again, they have the same incoming states, namely the 0 and the 1 here. Okay, so this is the model. And when I'm getting around to actually drawing partition functions and pictures, it's sometimes useful to have an alternative way of drawing the vertices. And indeed, in the combinatorial literature, you'll find any number of ways of representing the vertices of the model. And one of the other popular ways is to do it in terms of these particles and trajectories now. And so all I do there is I replace a 1 by a particle, and a 0 is just replaced by an empty space. And so if you do this, then you will get these 6 drawings that we have here. Okay, so this is the 6-vertex model, but the reason why this thing is actually stochastic has to do with the way that you actually choose these functions. So B plus, B minus, C plus, and C minus. So these are essentially the parameters that we have in the game. And what we would like to do is choose them in such a way that this actually translates now into a Markovian type of system. So you can actually think of it now as a probabilistic object. And so what we do is we'll choose these parameters now to live somewhere between 0 and 1. Right? And the second property that we'll choose is that when you actually add them up, so if I add up B plus and C plus and B minus and C minus, in both cases, I just get 1. And so this is nothing but conservation of probability happening here. So if we go back to the examples, or maybe let's look at the little figure that we have here. So here I have a particle which enters from below, and here I also have a particle which enters from below. And it has two possible things that it can do. Either it can go straight up, or it can turn to the right. And the probability of it going straight up is going to be B plus, and the probability of it going to the right is going to be C plus. And so in this way, whenever we see a vertex of the form given here, this thing is literally just a probability. So at all times, whenever you see a vertex with the 4 edges carrying some sort of labels, that thing should just be thought of as an honest probability. And here, I, j, k, and l at this stage will take values in 0 and 1. All right, so that's stochastic 6-vertex model. And so in the, not so much in today's lecture and in tomorrow's lecture, but in the final lecture on Thursday, I will be saying a little bit more about some other types of vertex models, which are so-called colored stochastic vertex models. And so that's the reason why I'm introducing them here. And so they look actually rather similar to the 6-vertex model, with the exception now that the states that live on the edges of the vertex now, these are going to be no longer taking values in 0 and 1. They can now take values in 0, 1, all the way up to n. So there is some extra natural number which is in the game now, this n. And this thing is actually related to the rank of the underlying quantum group. So I didn't say it before, but 6-vertex model is very naturally related with quantum group UQSL2 hat. And if you take that quantum group and take the natural high rank extension where you replace SL2 by SLN, then the corresponding model that you get is precisely this colored stochastic vertex model that I'm looking at here. Okay, so I have now these are the possible types of vertex that I can have here. So here we're assuming that I and j can take values between 0 and n. And I'm also assuming here that I is actually less than j in order to distinguish the different types of vertex that I have. So if I look at the first one, well, this one here, in the case of the 6-vertex model, this was either the vertex that had all zeros or it's the vertex that has all ones. And in both cases, the weight that you should prescribe to this is just going to be 1, because of the fact that in this case, there's no freedom whatsoever. Nothing can happen. The two colors that come in have to leave via the top and the right edge of the vertex. And so it's completely deterministic, and that's the reason why it gets the weight 1. But once again, if I look at the remaining ones, they are the interesting one, and we can see that, well, here, this vertex, again, will pair naturally with this one, right? In the sense that the incoming states here, I and j, which are now some integers, they are the same in both cases. And what we're looking at here is the probability that either they're going to switch with each other, as they did here, or they're going to sort of bounce off each other, as they did here. So yeah, once again, you have some vertex model with particles that are propagating through the vertices. And once again, there is a conservation rule that whatever enters has to leave. Okay. And obviously, when square is equal to 1, we just recover 6-vertex model. So this model is just a more general version of 6-vertex model, where the states are now, you can think of them as being like colored particles. And once again, when we're drawing the pictures, it's sometimes useful to use the particle and the trajectory notation, which again looks like this, and pretty self-explanatory in view of the pictures that we have above. Okay. And once again, this thing is giving you honest probabilities. Once again, we choose the B plus and the C plus such that when you add them up, you get 1, and we're choosing the other two such that when you add them up, you get 1. Okay. So this is those are the two models that will be the foundation actually for what we're going to talk about in the lectures. And what we wish to do actually is to endow them with a little bit more structure. So as I've stated them so far, these weights here, they're absolutely arbitrary. They could be anything, provided that they satisfy the necessary probabilistic conditions. But what we would like to do is put a bit more structure into it. And so we do that by actually now parameterizing those weights in such a way that we get an integrable model. All right, so I have those 4 parameters. And what we're going to do now is parameterize them in terms of 2 other parameters. So the first one is going to be denoted by a Z. And this thing in the literature, this is normally called spectral parameter, at least in the mathematical physics literature. And the Q here, this would be called quantum parameter. The Q is actually the same Q that shows up in the underlying quantum group structure. So yeah, so that's the reason why this thing is referred to as quantum parameter. And as we're going to see, this spectral parameter here, this is actually local in the sense that the spectral parameter, as you go from one vertex to another vertex in the model, the spectral parameter actually changes. So it's something that is a local quantity. But the quantum parameter, this is global. So this is actually fixed everywhere in the model. So all of the vertices have the same quantum parameter. Okay, so we would like to choose our weights in such a way that we get an integrable model. So the term integrable, at least in the context of integrable models, this is something that can have various ways in which is actually defined. So to actually speak of integrable model, you normally will have a varying definition depending on whether you're talking about a quantum integrable model or a classical integrable model. But for our purposes, we're going to take the definition of integrable to be a model that satisfies a Yang-Baxter equation. And so we're going to look at the Yang-Baxter equation in just a moment. And so now here is the explicit parameterization of those weights. All right, so as before, this first vertex here, nothing can happen, so it just has the weight 1. And now when we look at the remaining 4, we look at the partners that actually show up here. So this one and this one. So these are now some rational functions in the quantum parameter Q and the spectral parameter Z. And you can see pretty easily that when you add those 2 things up, you get 1, which is the property that we need for the model to remain stochastic. And likewise, looking at the 2 here, when I add those two up, I also get 1. So indeed, this is a parameterization that will preserve the stochasticity of the model. But there are deeper reasons behind actually taking this particular parameterization. And the deeper reason is the fact that we have the Yang-Baxter equation. So this is Yang-Baxter equation here, probably familiar to many people in the audience. So here I've given the, I guess, combinatorial version of Yang-Baxter equation in terms of these diagrams where I have these three conjoined vertices. But there are other ways of writing it. So there is another way that makes use of so-called R matrices, in which case the equation will be an equation that relates a product of three R matrices on the left-hand side to a product of three R matrices on the right-hand side. But this is sort of an algebraic approach that will be unnecessary for us, so we'll just use the diagrammatic version that's given here. So let's have a look at what this says. So first thing about this equation is it's actually not just one equation, but a very large number of simultaneous nonlinear equations. So the reason why you have the large number of equations is these parameters here, I1 to G3 that I have here, they can be chosen to be anything between 0 and n. So I can choose any integer values between 0 and n for those 6 parameters. And so actually, we then have n plus 1 to the 6 equations that actually arise out of this diagram that's being drawn here. So it's a large number of equations. And what happens here is these I1 up to J3, these are the states which are the living on the external edges of the 3 vertices that I have here. So looking at this collection of 3 vertices here, you can see that I1, I2, I3, and so on, I'm using these, assigning them to the edges that live on the exterior of this particular product of vertices. And the point is I have to then choose the same states on the right-hand side. So this I1, I2, and I3, they will be exactly the same as the ones that I choose on the left-hand side. So these are fixed to some specific values. And then what you do is you sum over the states that live on the internal edges of the vertices. So here I'll actually perform a sum over K1, K2, and K3. And so these are just dummy indices. And likewise here, I've given them the same names on both sides of the equation, but this should not cause any confusion. These are really just dummy indices. All right. And so there's one other thing about this equation which is important to note, and that is the dependence on the spectral parameters. So maybe I can just zoom in a little bit. So notice that the spectral parameter that is assigned to the 3 vertices is actually different in all 3 cases. So here it's going to be x divided by y, this is going to be x divided by z, and this is going to be y divided by z. And a natural way that you can actually think of how you actually assign the spectral parameter is to do the following. So I'm just going to delete some of this mess. So actually what you do is you can think of some variables that live along, that actually sort of propagate along the lines. So I can actually put a little x here, I can put a little y here, maybe I'll put an arrow as well. And on the final one, I can put a little z. And so once I put those labels in, I actually have a way of figuring out what is the spectral parameter for any given vertex. And the way you figure it out is you just take the ratio of the 2 variables that actually go through that particular vertex. So looking at this one here, well, here I have the ratio of x and y because those are the 2 variables that pass through the intersection that I have. And so this idea of assigning these extra variables which are just some indeterminates to the lines. This is an idea that we'll use a lot in the subsequent lectures. So it's a good idea to get used to that now. All right. Okay. All right. And as I said before, so even though the spectral parameters are varying as I look at the three vertices, the quantum parameter that we have, the q, is the same in all cases. So for every single vertex, the value of q is invariant. All right. So I did a little example here. Very often when you see Yang-Baxter equation, you see it either presented in the form that I gave up here, or you might see the algebraic form, but it's not always common that you actually see explicit example of how it works. So I just put in a little example here. I mean, the mechanics of this computation are quite trivial, but it's nice to see in practice how it works. So here we're actually just going to take n to be equal to 1. So in that case, we get back down to the usual 6-vertex model. And I'm going to choose the I1 up to I3, which I can think of as like the incoming states into this trivalent vertex. I'm going to choose them to be 1, 1, 0. And then for the outgoing states, I'll choose this to be 0, 1, 1. And actually, when you make these choices, you have to choose those vectors in a suitable way. Otherwise, you often just get a trivial equation. So it's fun to play around with these, but there are certainly some choices for the i's and the j's that give rise to just a trivial, almost tautological equation. So this is a non-trivial one. And so what we end up with is this. So on the left-hand side, what do I have to do? So I have to fix the i's to the values that we're given. So I have to fix to 1, 1, 0. And likewise for the j's, I have to fix to 0, 1, 1. So this has been done. And then you have to sum over all possible internal edge states. But when you perform this summation, you have to respect the ice rule. So you cannot produce a vertex that has configuration of states around it that is not satisfying the ice rule. And because of that constraint, actually on the left-hand side, there is just one possible configuration. Right? So this is a configuration where, well, I have 2 1s that enter into this vertex here. And because of that fact, they must also leave. So that forces these edges to be occupied by 1s. And likewise with the vertex that leaves, this one here that I just deleted. Here I have 1s which are outgoing. So again, that will force the corresponding incoming edges to be occupied by 1s. And once I've done this, there is no freedom left. So everything is just completely frozen. And so that left-hand side, what you would do is you would just compute it now as a product of rational functions. So it will be a rational function that depends on x, y, and z, and q, which you can explicitly compute. On the other hand, if you look at the right-hand side, well, we get something a little bit different. So once again, I have to freeze the external edges to the values that we have specified. But this time, when you actually look at what happens on the internal edges, there is a degree of freedom. So in this case, actually, you find that, say, the one that enters here, it has the choice of, say, propagating like this to its final destination up there, or it can just propagate like this. And everything else is basically uninteresting. But this gives us two cases here, which you then have to sum up. And again, both of those trivalent vertices here, you would adjust the compute as some rational function and then just add the two rational functions together. So this whole identity here, this is some non-trivial identity of rational functions in all of the parameters that we have. And if you look at these Yang-Baxter equations, you'll convince yourself that it's a highly non-trivial equation, because not only do you have to satisfy one such equation that we've given here, in the for the case we're looking at 6 vertex model, there's 2 to the 6 equations that need to be satisfied, and many of them are non-trivial in this vein here. So Yang-Baxter equation is certainly one of the miracles that really makes integrable models work. All right. Okay, so this is the setup so far. What I'd like to talk about next is well, embedding the vertex models in a certain geometry now. So there is a sort of natural thing to do, which is to place the vertex models in a quadrant. So we're going to study them on this subset of the integer lattice. And there are some probabilistic motivations for doing this, and certainly for many members of the audience, this is a very familiar topic. So I'll say a little bit about the probabilistic motivations, but really, I guess from the point of view of these particular lectures, I guess I'm more interested in really the algebraic point of view. So that is to say, really, the fact that when you put the vertex model in the quadrant, you can actually get out of it certain multivariate rational functions that have a host of very interesting properties. And I would say most of those properties actually descend straight from the Yang-Baxter equation that we just looked at above. So this Yang-Baxter equation really gives you a huge amount of mileage in terms of studying these models. All right. So we're going to look at 2 basic types of partition functions. Okay, so partition function, so this is something that has not been defined so far, so I'll say a little bit about what this actually means. But let's look at the first example. So the first example is where we choose some natural number n, and we then choose some subset of the naturals. So this k1 up to kn, these are actually going to be the coordinates of particles which are going to exit the lattice. All right. And so here we have the function that we would like to define. So it's going to be depending on that subset of coordinates, k1 up to kn. And we define it as this object here. So what's happening here? So I have a collection of n horizontal lines, and on each of the incoming edges of that horizontal line, we have a particle coming. So we have particles coming in on every single horizontal line. And then we have, say, an unlimited number of vertical lines that we have here. And all of these lines carry different parameters. So the horizontal lines will carry parameters which will be x's. So here I have done x1 up to xn. And likewise, the vertical lines will have some parameters which will be the y's. And just to remind you, when you compute the spectral parameter of a given vertex, what you should do is take the ratio of the horizontal spectral parameter and the vertical spectral parameter. Take the ratio of those 2 things. Okay, and so I guess the interesting part of this object here is what's happening at the top here. So like I said, the Ks, they are actually labeling the coordinates where the particles actually leave. So for this particular example, this would be where K1 is equal to 2, this is equal to 3, 4, 5, 6, I think this one is going to be 7. So these are the coordinates where the particles leave. Okay, so how do you actually compute this object? Okay, so what you have to do, and for all types of partition functions that you meet in the 6-vertex model, you actually have to draw all possible configurations. Right? So for this particular example, one possible configuration could be something, say something like this. For example. So you actually have to trace out all of these particle trajectories, and every single set of particle trajectories that you have, you then compute the weight of the corresponding lattice quantity that we have. And that gives you some big rational function. And then you have to work out all possible configurations and add together all of those rational functions. So in principle, this is a very complicated object, enormous rational function that is very difficult to compute explicitly. All right. But the reason why we're interested in this type of object, actually come to it below. Well, one reason why people might study this type of objects is it actually has links to certain types of stochastic processes that are very well studied. And so one of the more well-known links that we have here is I can actually take the situation where I have a large number of incoming particles now. So I effectively take the number of incoming particles that are entering the lattice. I can take this number to be very large, essentially approaching infinity. And what I also do is say set all of these y parameters to the value 1. And then I take the x parameters and I take these to be very small. So you have the situation where you have a large number of horizontal lines and you have x parameters that are very, very small. And under this scaling, what happens is the configuration of particles that I have along the top here now, this is actually going to converge to the distribution of particles in the RCEP, so the asymmetric simple exclusion process, which is one of the most well-studied stochastic processes, exactly solvable stochastic processes in one dimension. So there is a limit of these type of two-dimensional objects to these one-dimensional stochastic processes. So this is one motivation why you might choose to actually look at this type of quantity. All right. And so there's going to be a second type of object that we're going to look at. So again, not so much in today's lecture and not so much in tomorrow's lecture, but primarily in Thursday's lecture, we're going to look at versions of the partition functions where the particles become colored now. So in the colored situation, we have a little bit more information that we actually have to encode. So once again, we'll have some subset of the naturals that will tell us the coordinates of where particles leave the lattice. But you also have to put in some extra information, which are going to be two vectors, which we call mu and nu. And so these are just living in Cartesian product of 1 to n, taken capital N times. And those two vectors satisfy the property that when you sort the components, so that is to say, when you arrange the components in decreasing fashion, they satisfy the property that their sort is actually equal. And so we can actually refer to this as the the partition ordering of those particular vectors. All right, so this is the setup, and I get this kind of picture here now. So for this function now, I'm going to give it a little bit more, a few more labels on it. So again, I still have the coordinates which are labeled by the k's, but now I also label it by these two vectors. And so what's happening here is I have particles that enter along each of the horizontal edges that we have along here. But the particles that enter, they can have different colors now. So this is now living in this colored stochastic vertex model. And the way that I encode the incoming colors is via those two vectors. So the first vector here is the vector of the mu's, and this is telling me basically the collection of colors that I have incoming. And likewise, the vector nu that lives up here, this is telling me the collection of colors that are leaving at the top. Okay. So this is the colored setup. And like I said, we'll return to this in Thursday's talk. Okay. So I don't know how we go with questions in these lectures, but I can pause.
So somebody was asking questions in the chat, and somebody else was answering them. So far, nothing there was no need to elevate the questions to you at the moment. But if you want to look at the discussion, there is something in the chat, and then other people. It's also fine for people to unmute themselves and ask questions live, but so far chat has been the prevalent medium for the question.
Yeah. Okay, so I won't read it now, but yeah. If at any stage there is a more pressing question, then I hope people will just
But in case you're wondering if people are listening, people are listening and they are chatting. Okay. So
okay, no. Okay, good. All right. Okay, so let's say something about the properties of these partition functions. So, well, the first property that we would like to highlight is they have some nice sum to unity properties. So, okay, so let's look at the first one. So this is the function capital F, which was defined up here. Now I've drawn all over it, but yeah, this was the one where it lives in the 6-vertex model. Okay, so this is the case where little n is equal to 1, and we have particles that are all black, and they enter and then they leave somewhere at the top. All right, so for this quantity here, it satisfies the property that if I sum over all possible subsets of the naturals, then that thing is going to sum up to 1. Okay, so why is this true? Well, this is true because looking at the situation we have up here, maybe I'll use just a different color. So those particles, they're entering along here. And what we're doing is we're looking at how they're distributed along this horizontal line here. That you can think of this horizontal line as just extending all the way out to infinity. And so what's happening is you have the particles coming in, and they have to go somewhere, right? We know that we have a conservation property of the model. And so those particles have to situate themselves somewhere along basically this orange horizontal line that I'm drawing here. And just by looking at all possible ways that they can situate themselves along there, that is precisely performing the sum over all possible subsets of the naturals. And because we know that every single configuration, such as this configuration here, this is an honest probability, right? This is really computing for you the probability that this particle travels along here, and this is computing for you the probability that this one travels along here. And so because of the fact that every single configuration is an honest probability, it must be that when I perform that sum over all subsets that live along the horizontal line up here, must be that it adds up to 1, just by conservation of probability. So that's the first property. And if we look at the sum to unity in the case of the colored model, in that case, we have to perform 2 sums. So the first sum is again over all possible subsets of the naturals. That's as it was before. But now we have the second sum, which is going to be over the ensemble of colors that leave via the top of the lattice. Okay, so what I'm doing here is I'm summing over all possible vectors of colors at the top, such that the sort of that vector is equal to the sort of the incoming vector. Okay, so it's stated in a less cumbersome fashion. If we look at this example up here, when I perform that sum, I would actually have to sum over all possible ways for those colors at the top to rearrange themselves, to permute their order. So here, let's actually try to maybe do it. So one other version of this, let's try this. Okay, so here is another version in which they could permute themselves in this particular order. Okay, and then we'll have to sum over all other possibilities. So this is the secondary sum that's happening here. It's summing over all possible ways for those colors to permute themselves. And once again, when you compute those 2 sums, it must be that when you add the thing up, it has to sum up to 1, just by the stochasticity of the model. Okay. But actually, looking at this, there is something that's a little bit deeper than that, which is interesting to note, and that is, if we look at this double sum that we have here, what can we actually say about the second sum that we have here? And actually, there is, in a sense, a refinement of the stochasticity property, which is usually referred to as the color blindness property. So what the color blindness property says is that second sum that we have here. So here I've just directly translated the thing that was in the brackets up here. So that sum, where I sum over all possible ways of permuting the colors of the lattice while keeping the coordinates fixed. When I actually perform that sum, what do I get here? I actually get nothing but the capital F. So the first time you see this identity, it's kind of striking, and it has a relatively simple proof, but it's certainly a striking fact that if I take the quantity that I have up here, and if I now perform this sum over all possible ways of permuting the colors at the top while keeping the positions fixed, what it's saying is of all possible ways of permuting it, I actually get nothing but the black and white partition function that we have here, where the colors are completely vanished, and what I have now is just the actual coordinates where the colors leave. So this is the idea of color blindness. And the thing about the color blindness is it's actually independent of the ensemble of colors that I have coming in here. So those colors that come in there, they could actually be absolutely anything, provided I sum over all ways of permuting them at the top, you will get the color blindness property. So that's the reason why I stated this. This actually holds for all vectors mu that enter along the left edges of the lattice. So this is color blindness, and from the color blindness property, you can see actually that, actually these two sum to unity properties now, they're exactly the same, because if you use color blindness in the second one, it just collapses to the first one.
I have a quick question.
Yep.
So the capital F is SL2, related to SL2, and the lowercase f is SLN?
Yes.
So how do you think of the color blindness in terms of SL2 versus SLN?
At the level of the algebras, yeah.
Yeah.
So this is a good question, and actually one that we're still trying to figure out. Yeah, so my understanding of it is it must have something to do with possible ways of embedding one of the algebras as a subalgebra of the other one. But unfortunately, I don't have anything more precise to say in terms of how you can explicitly see this at the level of the algebras.
Okay, yeah. That helps. Thanks.
Yeah, it's a good question, and certainly one that is worth asking. Yeah.
Thanks.
All right, so so this was color blindness. All right, so now I'm going to move on and talk about another property of this object, which is its symmetry. So, all right, maybe a change of color. Okay, so here's the proposition. So this capital F function, which we have defined in SL2 model, this is actually symmetric in the alphabet of the x's. All right. So I included this in the lecture because this is a really classical argument that is so ubiquitous and useful in integrable models that for anyone who hasn't seen it, it's just good to see it as soon as you can. So I hope this will be the first time someone has seen this. So this is sometimes referred to as the unzipping argument. And so effectively what we're going to do is we're going to take this partition function, and we're going to show that it is invariant when you exchange two of its rows. And so actually for the purposes of doing this, it's sufficient to take the rows to be neighboring rows. So they're going to be next to each other. And obviously if you can prove this invariance for nearest neighbor rows, then you can prove it for any permutation of the rows. Okay. All right, so here is the argument. So we start off from the picture of the partition function, and we're going to be focusing on these two rows here. So that have the variables xi and xi plus 1. All right. And I've put some kind of state along the top of the lattice. So this is corresponding with the k's, which are the coordinates. But actually the state that you put at the top, it plays actually no role in the argument whatsoever. And so that's the reason why we actually get the symmetry for the whole family at once, because that state here is not playing any role in the following argument. So really the thing that matters for the argument are the states that live along here and along here. This is really the essential feature. All right, so now we're going to do the first step. And so the first step is a little bit sneaky in a way, but the idea is you would like to use Yang-Baxter equation in order to actually exchange those two rows somehow. But you can't use Yang-Baxter equation on just this partition function you have up here. You need to introduce an extra vertex into the picture somehow, such that you'll get one of these trivalent looking things. So you can actually do Yang-Baxter equation. And so the idea is you put the vertex here at the, well, I've put it at the right here. And so the idea is when I put this vertex into this picture here, the claim is that it's actually equal to the partition function that we had above. And the reason why those two pictures are equal is that inserted vertex, this is actually just completely frozen. There is no degree of freedom here. So if I look at this guy here, I have two, oh, let's try that again. I have here two zeros, which are the, say, the exiting states of that vertex. And by conservation property, that means that these must be zeros as well. So actually that vertex that I've introduced, there's nothing going on. It's just completely frozen. And furthermore, the thing that it freezes to, this is just the vertex where I have all zeros. And the vertex where I have all zeros, this thing has weight 1. So really all I've done here is just multiply my partition function by 1. I didn't do anything so far. And the next idea is to now take that vertex that has been introduced, and we're going to move it now in the direction of the arrows here. So we're actually going to push it through all the way to the left of the lattice. And so this is the unzipping part of the argument. Okay, so we're going to drag it through, and we'll use Young-Baxter equation in order to do this. And you can see that here we're set up to use Young-Baxter equation, because looking at this vertex here, you can see that the 3 marked points here, here, and here, this is precisely the type of configuration where you have a Young-Baxter equation. And so I can start moving this cross all the way through towards the left. And so if I do that all the way to the bitter end, then I'll end up with this picture here. So in this picture, what has happened, that extra vertex has migrated all the way to the left. And now let's zoom in and look at it. Well, looking at this vertex, once again, we actually see that it's just frozen. So why is it frozen? Well, again, I have these particles which are incoming, and they're incoming along both of the incoming edges. So this is just frozen to this configuration here. And that is the vertex which is completely occupied. And again, that thing has a weight 1. So you can remove that vertex now. And once you do that, you will get the final picture here. And so this, in this final picture, exactly the same partition function that we started with one important difference. And that is those two variables, xi and xi plus 1, have actually switched their order. So just like this, we've managed to prove the invariance of the object under exchange of those two variables. And this is sufficient to prove the symmetry of the corresponding rational function. So yeah, moral of the story, even though these f functions are, on the surface, extremely complicated objects that look like they don't have a lot of structure, Young-Baxter equation already gives us one fact about them, which is the fact that they're actually symmetric in their full alphabet. And in a way, that symmetry, if you're just coming into this problem completely cold, just looking at the way the thing is defined, it almost seems inconceivable that this thing should depend on x1 in the same way that it depends on xn. Right? This is absolutely not obvious, but Young-Baxter equation tells us that all of them are on equal footing. Okay, so that brings me to the final part of what I wanted to say today. And that is an explicit formula for those f functions. So the motivation for giving this explicit formula, well, we're going to need it in the next lecture when we actually talk about whole Littlewood polynomials. But also it's a formula that I think has a lot of, well, it's a very non-trivial formula, and it also has some historical significance in something which is called beta ansatz. So really the exactly solvable quantum models, this is a topic that is very, very old, going all the way back to the work of Bader and Schrödinger in the 20s and the 30s. And so this type of formula that I'm about to write down here, this is a formula that you see in when people do beta ansatz for these type of models. Okay, so here is the formula. So again, for all subsets of the naturals that we choose, we have the following formula.
Okay, it seems that Michael has disconnected.
Am I back? Yeah.
The formula overwhelmed the internet.
The formula overwhelmed the internet. Yeah, that's right.
Okay, no, apparently not. Okay, good.
That's Australian internet at its finest. Okay, so now I'm going to try to.
Yep, it's in process. I'm not seeing the okay, now I'm seeing the image. Yeah, okay, good.
Okay. Okay.
Yeah.
So I don't know what I got up to before I cut out, but yeah. So this is the object that we want to study. So this f that depends on these coordinates k1 up to kn, and so here is the formula. So what is the formula? So the formula is going to be summing over all elements of symmetric group. So I'm summing over all permutations in Sn. And the thing that I'm symmetrizing is this product here, which kind of complicated looking product, but actually when you look at it, you realize it's actually not that bad. So the first factor that we have here, this is what physicists refer to normally as a scattering type factor. So this is, well, I'll say a bit more about it in a second, but this is the factor which actually, in a sense, connects up the various one particle contributions that you have. So if we did not have this factor here, then this formula would actually just be completely trivial and just completely factorized out. So this is the thing that really, it's like the glue that ties together the one particle contributions. And then we have this contribution here, and this is the aforementioned one particle contribution. So I'm making a product over all of the particles from 1 up to n. And the thing that I have here then is some other product. And so you see that these coordinates appear basically as the terminals in that product that we have here. And what I have there is just some rational function in the parameters. And the way that the permutation acts, so sigma is just acting on the alphabet of the x's. So acts in the obvious way, sigma acting on 1 up to x is just going to just permute the x's. So in particular, sigma does not have an action on the y's. The y's are like spectators compared with the sigma. Okay, and so one way of, I guess, motivating this formula is to look at the n equals 1 case. So in the n equals 1 case, the formula simplifies drastically. In that case, we don't even sum anymore because we just sum S1 and we get this. So here I have f that depends on a single coordinate, k now. And in that case, I just have this expression. All right. And actually proving the n equals 1 case is very simple. All you have to do is draw the corresponding picture. So here is the picture. So what do I have? So I have a single particle which enters from the left and it goes out somewhere at the top at coordinate k. And its trajectory is completely determined. It has nowhere else to go. And so what you end up getting is a product of vertices of this type here. So this is one of these, I think I referred to this as a B- vertex at the start of the lecture, and the weight of this thing should be something like 1 minus z over 1 minus qz, where z is the corresponding spectral parameter. And just to remind you, the z is the ratio of the two parameters that go through the vertex. So for the very first one, it's going to be x1 over y1. It's going to be the spectral parameter of that very first vertex here. And so from that little picture, you can very easily see now where this first factor comes from. And the final factor that we have here, that is coming from this vertex here. And so that vertex, I would have called that C minus. And the weight of the C minus will be exactly what's given here. And all of the empty vertices at the end, they don't contribute in any way. They just all have weight equal to 1. So once you have the one particle case, it's very natural then to come up with an ansatz where you multiply all of those one particle configurations and you try to mix them or combine them in a non-trivial way, which is done precisely via this scattering factor here. So this is a kind of ansatz, which is normally referred to as coordinate beta ansatz, which you can, once you write down this formula, you can subsequently verify that it is true. But yeah, we're not going to go into the proof of that particular formula. However, this is an important formula, and really for the purposes of these lectures, I really wanted to emphasize that just starting from this, one of these most basic quantities in the 6-vertex model, from this you can actually derive those families of symmetric functions, the whole Littlewood's, the q-Whittakers, and even the McDonald polynomials are all somehow just descending from this little formula that's written here. And so this idea of constructing these symmetric functions actually directly from this formula here for the wave functions, this is an idea which is, I guess the details have only really been fleshed out in sort of the last decade or the last 15 years by various authors. And so I think it's worthwhile trying to publicize that a bit more in these talks. So, all right. So I guess that's probably coming to the end of my time. So can take some questions.
So yeah, there are two last questions in the chat that I haven't had time to answer yet. Maybe you could look at that. That seems like natural. Okay. Well, let's first thank Michael. At least I can clap with the sound. But not just me. And then please think about questions you might have while Michael reads and answers the last two questions on the chat.
Okay, reference for this formula. This is a good question.
This is probably the paper of Leo and myself on inhomogeneous.
Yeah, that's.
So
I was wondering if there was a earlier reference, but I don't think so.
There is probably, yes, there should be such formulas, and for example, the work of Varchenko and Felder, although I would need to look for references. They call these things weight functions. I'm not 100% sure they have column inhomogeneities there. But there might be, I'm not claiming that our paper is the earliest, but I'll give a link in the chat as one of the possible references.
Yeah, I think that's certainly probably the clear. Okay, is there a similar proof for the colored case? So I assume you're referring to the symmetry argument that I gave, Young-Baxter argument. So that's a good question. So in the colored case, so let's actually go back to the pictures that we had. In this case, you would like to repeat the argument. So we would like to put, a vertex in here and then insert it through and ultimately delete it. The issue with doing this in the colored case is you're not going to have any problem adding that vertex. Right? So if I add this vertex on the right that I have here, I'll be able to add it for free because once again, these states here are all zeros, right? So I'll be able to put it in and once again, it will be frozen because of the fact that they're all zeros. The problem will arise when it actually comes out on the other side. So when it comes out on the left, it will appear, it'll look something like this. So I'll have this sort of object. The red here and blue here. And so that object there, that is not going to be frozen because that vertex, there are two possibilities as we've seen. So either the blue will go here and the red will go here, or the opposite. And so that means that you cannot simply delete that vertex. And so that means in particular that these functions that we have here, these are actually not symmetric. They do not depend symmetrically on their alphabet x1 up to xn. Okay.
And there is one more question in the chat.
Yeah. What is interpretation of F in the ASEP? Yeah, that's right. So I mentioned it briefly in the talk. So in your F, what do you need to do? So you will set all of the y parameters to some value, something like 1. You will set all of the x parameters to something small, and then you'll take the number of horizontal parameters to be large. And the claim is when you do this, the configuration of particles that you have along the top, this partition function will then converge to the probability of seeing, a particle at this position, etc. There is a slight caveat in that, in the sense that actually the frame of reference is sort of traveling. So the origin in your ASEP is actually drifting to the right at constant velocity. So yeah, but there is certainly a claim where the F will recover for you the ASEP probabilities. Yes.
And that's at some fixed time, and the fixed time you get depends on how you let the x's tend to 0 or something like that?
Yeah, that's right. It will be at some fixed time. Exactly. Yes.
Okay.
Yeah.
Thanks.
Yeah, the time will depend on how high you observe the configuration. So that it depends on the height of the model that you're looking at.
And here we've got height. The pictures Michael's been drawing have got height. We haven't got any. We've just got height 0 essentially. I'm not sure I understand what you mean by the height of the configuration in terms of the pictures.
Well, so that's n capital in the pictures that Michael is drawing. There are a total of n rows. So that n, when scaled, gets transformed into ASEP time.
But then these F functions, they themselves are not describing transition probabilities for ASEP. Because they depend on n.
They're not describing transition probabilities. They're they're describing the probability of seeing the system in this configuration, given that it started in the step initial condition. Yeah, if you want transition probabilities, then you would need to put you know, some configuration of particles at the bottom as well, and then in that case, this will give you honest transition probabilities in either in RCEP or multi-species RCEP.
Mm-hmm.
Okay. Any other questions, Michael? Okay, let's thank him again, especially since already after midnight in Melbourne, he worked hard. And I enjoyed the lecture. I hope everybody else did too. So Michael will continue tomorrow at the same time. And today our second lecture will be the second lecture of Fabio Toninelli in about 40 minutes. So that's 11 a.m. in East Coast US time. Hope to see you there. I think that this Zoom window will remain open for the next 40 minutes, but we do have a break. So.
Okay. Well,
thank you, Michael.
I'll probably get